Hey guys, it's your favorite reliability and test guy here with another fun-filled, action-packed video on reliability tests and validation topics. This current video is an introduction to accelerated life testing, how subsystems and systems are accelerated to speed up learnings. I hope you enjoy this video, and if you do, don't forget to hit that like button and subscribe to my channel. Thanks for watching, and let's get started! In this video, we will cover definitions, how tests are accelerated, and examples of applying accelerated factors to tests. Let's go ahead and cover some definitions now. So what is accelerated life testing? Accelerated life testing is a method used in reliability engineering to determine the end of life and confirm predicted failure modes during the wear-out period. Accelerated life testing is a practice used in reliability engineering and is used to determine end of life and confirm predicted failure modes during the wear-out period in a reduced amount of test time. Accelerated life testing can also be a useful tool for determining if components or a subsystem within a system achieve the desired predicted wear-out period or do not fail within the warranty period or at the infancy of operation. Let's briefly cover the good old-fashioned bathtub reliability curve. The vertical axis represents failure rate, while the horizontal axis represents time. The horizontal axis can also represent things such as cycles or miles as well. The bathtub curve can be broken up into three regions: early failures or infantile mortality region, operational region where the failure rate is constant, and the wear-out region or end-of-life region, where the system begins to degrade as a result of age and years of stress and fatigue due to normal operation. Let's go ahead and cover tests for assessing where a system currently falls in the current configuration on the bathtub curve. First, we have the HALT, or Highly Accelerated Stress Test, which tests for design margin but does not give you a quantifiable life value, but does give you a value to determine where your design stands in regards to the operational stress input and the margin that you are testing for and you have found for your design. A derivative of highly accelerated life testing is HAS, or Highly Accelerated Stress Screening. HAS testing is used to screen for latent defects in production to prevent systems from escaping into the wild just to break down or fail in early operation. Another type of reliability test is a full life test. This is where you literally run every hour or cycle that the part will be subjected to for its lifetime until it breaks. Now, many systems and products will be used for around 8 to 12 hours a day or even less, and some products will only be used for up to 5 days a week or perhaps even less. This will allow you to be able to create a test that will allow you to run 24/7, which will help cut down some of the time for testing. However, depending on the period of time that needs to elapse to determine the wear-out period, it could still take years to complete this type of testing, which isn't practical from a product development life cycle perspective. With that being said, it could be worthwhile to run this type of test independently of the product development life cycle as an ongoing reliability study. And now we come to the pinnacle of reliability tests, accelerated life testing. Accelerated life testing is great because you can compress the amount of time required in order to determine where your product falls on the bathtub curve, and you will be able to determine a mean time to failure value in a much shorter amount of time. Let's look at how life data is modeled and analyzed. Life data does not fit into a normal distribution typically, which is why you will often hear the term Weibull or Weibull analysis when someone refers to life data analysis. Weibull curves are plotted against vertical axis, which represents failures, and a horizontal axis, which represents time. Here is an example of Weibull curves. The first curve has a steep downward slope, which indicates the system has a short life expectancy and is prone to early life or infantile mortality failures. The slope of a system life model with early failures has a beta of less than 1. The second curve has a slope which flattens out into a plateau. This indicates a product or system that fails during the operational period. The shape of the curve has a beta that is equal to 1. The third curve has a upward slope. This indicates a product or system that fails during the wear-out period. The shape of the curve has a beta greater than 1 and has the desired point of failure that you would want to see in a system's life model. If you would like to learn more about Weibull analysis, check out my video. That is practical and conceptual video on Weibull analysis. Let's go through each of the reliability tests we just introduced quickly. Highly accelerated life testing uses step stress methodology to determine the operating limit and destruct limit independently for temperature, electrical, and vibration stresses as applicable. Ultimately, all three stresses are combined in a final test to run multiple accelerated cycles to determine if you've identified the design margin values for your system component or subsystem. You can use this data to derive a Haas test that can be used as a production end-of-line test to identify latent defects. Keep in mind, however, HALT cannot be used as the only test to assess your system's long-term reliability. Here are a few things to keep in mind with HALT testing. HALT does not determine life, only design margin. HALT assesses design margin and provides learnings to improve designs, but does not give you an MTTF or MTBF value. In summary, HALT determines if a system has enough margin built into the design to survive operating stresses encountered during use or operation. Check out my video on HALT and Haas testing to learn more about these reliability tests. Let's discuss full life testing now. Full life testing is the performance of normal operational stresses for the number of predicted cycles, hours, or miles, and so forth that the system will endure during its life in the field or in customer's hand. Full life testing is ran for the entire operational life period and can take a very long time and can even take years, and that is assuming that you aren't just running a system for its daily operational window and are cycling or operating a system 24 hours a day, 7 days a week, until the desired target is reached for metrics such as number of cycles, hours, or miles. Full life testing might not be feasible to perform, as the testing will most likely exceed the system development life cycle or product launch period. With full life testing, acceleration factors are not used, as the accelerated life testing simulates fatigue and wear out in a shortened amount of time by increasing the stress levels. Alright, let's jump into the core content of this video now. Accelerated life testing. Accelerated life testing simulates fatigue and wear out in a shortened period of time by increasing stress levels. Accelerated life testing can help you confirm potential failure modes based on the predicted cause or stress input. Identify the time to failure using an acceleration factor to reduce test time. Only one acceleration factor should be used as a stress input. Quick note to take care of when using a reliability and confidence parametric equation. If you are getting your stress levels from a test standard, the levels may already be accelerated. Therefore, if you do not know the acceleration factor that is used for that test standard and how the stress levels are produced and the durations are created, do not use an acceleration factor with that particular standard. The reason for this is that you do not want to apply an acceleration factor to an unknown already accelerated stress, as it can produce unrealistic or unrepresentative failure modes that the system will never see out in the field. To summarize, by increasing the stress input to a level above operational field stresses, you are able to reduce the amount of test time required to collect life data, which is called time compression. The following graph demonstrates the inverse relationship between time and stress. With an increased level of stress, you require less time to test for life of your system. However, as you decrease the stress levels, a longer amount of time is required to determine the life of your system. We have been talking about stress, so let's go ahead and cover a few types of stresses that can fatigue a system. Types of stresses include temperature, only or with humidity, acceleration, vibration or shock, compression, tension, fluid and gas pressure, and electrical stresses. There are equations for developing an acceleration factor for time compression to a reliability test for all the types of stress inputs we just talked about. Again, keep in mind that there's a limit to how much you can accelerate tests by increasing stress levels. You need to understand the design margin and safety margin for your system so that you do not produce unrealistic failure modes or create an unintended safety event when your system is destroyed by severely high and abusive stress levels. Many standards that cover time compression and acceleration factor calculations will provide recommendations to the maximum ratio of accelerated stress that can be applied over the operational stress limits. However, you also need to know and understand the limitation of your system. Here are a few things to keep in mind with accelerated life testing. Know the limits of your system ahead of time via design margin testing such as HALT. Standards that cover acceleration factors typically have a magnitude of limit for increasing stress or compressing test time. Only accelerate one stress input for an accelerated life test. Let's go ahead and cover some examples of how to accelerate a stress input into a system to reduce testing time. The first accelerated life test example is the constant temperature soak. The original Arrhenius equation used a gas constant instead of an activation energy and was used for analyzing the chemical reactions at the atomic level and molecular level phenomenons. Pictured is the Arrhenius equation for reliability. The Arrhenius equation for reliability uses activation energy, which is expressed as EAA or apparent activation energy. Activation energy is the amount of energy required to cause a chemical reaction or some other physical reaction of a particular material. When you cook a steak, for instance, you are beginning with a raw slab of animal muscle. As you heat up the steak, it begins to react to the heat and oxygen in the air as the activation energy is reached and begins to turn brown. Cook the steak too hot or too long will cause the steak to turn black and overcook, making it tough to chew and not pleasant to eat from a flavor standpoint. This is a great example of what happens when you apply too much stress. You can think of your system as the steak. If you increase the temperature too high, you can destroy your system and produce a none-field representative failure mode. Applying too much stress can even produce a safety event, and the system can even catch on fire depending on the temperature you are using and the components of your system. Another way to think of activation energy is with another analogy. Say you have a sledgehammer and you want to break a concrete cinder block. If you do not strike the cinder block with an adequate amount of energy, the block will not break, but you might get a nice jolt up through your arms as the energy bounces off the block and travels through your arms. However, if you strike the cinder block at the activation energy, it will fracture and break and fall apart. Additionally, if you strike the block too hard, you may go straight through the cinder block and end up striking the ground below the cinder block, which can also give you a nasty jolt through your arms, depending on the type of surface you end up striking. These three examples with the cinder block represent undertesting due to not reaching the activation energy, achieving the activation energy, and getting the optimal results that you were targeting, and overstressing the cinder block and producing an undesired effect by going well beyond the activation energy required to break the cinder block. To summarize, accelerating the temperature test requires an understanding of the activation energy for the materials and the components used for your system. You can either get information on activation energies from your supplier from experimentation or from activation energy tables for the materials for your system or part. Be careful using a general rule of thumb or general exponent for activation energy. If the general constant is not a close approximation of your system's activation energy, you could end up either not developing a profile that achieves the activation energy of your system, or you could end up burning your steak, using the analogy we just discussed. Let's go ahead and define all the variables and constants for the Arrhenius equation for reliability. AF stands for acceleration factor, as you might have guessed. This is the value you are solving for in order to accelerate your test or compress the test time. E is the natural log base. Again, EAA is the apparent activation energy. K is the Boltzmann's constant for activation energy, which has unit of measurement of activation energy over the temperature unit Kelvin. And as you might have guessed, T represents temperature and is expressed in kelvins. Remember, Engineering 101 here. Know what units your equation is in And don't be an idiot and use this equation to solve for Celsius or Fahrenheit without converting to kelvins. In order to use this equation to accelerate your constant temperature test, we need to split up the temperature variable into two temperature values, as pictured. T1 represents the test temperature that you will use for your test. T2 is the operational or field temperature that your system will be subjected to during its operational life. It should be pretty obvious that your T1 temperature value should be higher than your operational T2 value, but I just wanted to point that out just in case. All right, let's go ahead and run through a scenario. Pictured is a well-illustrated widget that needs to be tested. Pretty high-tech looking, huh? Yeah, probably not. Okay, so this is the widget, and it is expected to operate at 40 degrees C for 3 years. The 3 years target also happens to be our warranty period. Imagine that. The highest temperature that the widget can safely operate without being destroyed or damaged permanently is 90 degrees Celsius. Manager Mike wants confidence that the widget will survive past the warranty date of 3 years. The widget is launching in 6 months, and Engineer Bob has 3 months to determine if any design changes need to be made to the widget design. Bob needs to run an accelerated life test in 3 months that will predict 3 years of thermal stress on the widget. Looks like a tough situation for Engineer and Bob, huh? Well, not really. This is pretty easy to accomplish by using the handy-dandy Arrhenius equation. Let's go ahead and write out the values for each variable and constant in our equation. EAA equals 0.5. This is just an arbitrary value that I've selected for this example. Don't take this value and randomly plug it into your equation, and don't tell your boss when you do that the reliability and test guide told you that your EAA should be 0.5, because I didn't. This is just an arbitrary value used for this example. K equals 0.0000862. This is the Boltzmann's constant as we just discussed earlier. T1 equals 90. This is our maximum allowable test temperature. T2 equals 40. This is our operational or field temperature for the system that it will encounter in the field. Let's go ahead and plug in these values and see what happens. All right, we're plugging them in. So solving, we end up with an acceleration factor of 12.811. Recall that we had an allowable test time of 3 months, which comes out to 2,160 hours. Plugging in our test time duration and using our acceleration factor, we get 27,671 hours, which is approximately 3.16 years. Sweet! Manager Mike will be happy, and Engineer Bob should give himself a pat on the back. Here are some takeaways from the example we just covered. Using the acceleration factor, 3 months of testing provides a life prediction of 3.15 years if all test samples survive. Here are some pointers to keep in mind. Select a sufficient sample size. Don't be an idiot and use one sample. The mean time to failure value you come up with will be meaningless unless you end up testing to multiple lives using the parametric binomial equation and confidence equation, but then your test will run past 3 months. Continue to test if failures do not occur at 3 months if you can. You should figure out what the mean time to failure is, as this is a good value to acquire, as you can use this value to extend your warranty duration for future product lines and look at ways to reduce the design margin for your product, as it is obviously over-designed if it goes past the warranty period. Number 3, monitor the testing daily to look for any early failures. Don't be an idiot or lazy and start the test and come back 3 months later to see what happened. Manager Mike will not be happy in the event that something happened or failed and you just wasted 3 months. All right, let's go ahead and accelerate another type of test, temperature cycling. Pictured is the Coffin-Manson equation. Let's go ahead and define each of these variables for the equation. AF, of course, equals acceleration factor. HT test is the highest temperature set point for the test. LT test is the lowest temperature set point for the test. HT op is the highest temperature in operation or in the field. LT op is the lowest temperature in operation or in the field. M is the Coffin-Manson exponent or mechanical fatigue due to temperature stress. Oh boy, let's do another example. A widget that is installed externally on an aircraft that makes short trips between two high-temperature locations. When on the ground, the widget is exposed to a temperature of 40 degrees Celsius, and when airborne is exposed to a temperature of minus 44 degrees Celsius. This cycle occurs 6 times per day. The part is expected to operate for 10 years before the replacement interval. The widget can safely handle temperatures up to 120 degrees Celsius and as low as negative 70 degrees Celsius. The amount of test cycles we need to test for can be found by multiplying 6 cycles per day times 365 days times 10 years, which comes up to 21,900 cycles. Design an accelerated test to determine if the widget has a life that survives 10 years, which is the target wear-out replacement period. We need to know the Coffin-Manson exponent, or the mechanical fatigue due to thermal stress value for your system. Pictured is an example of a table for a range of exponent values based material properties. Plugging in our known values, we get HT test equals 120 degrees C, LT test as negative 70 degrees C, LT top op as 40 degrees C, and LT low op is minus 44 degrees Celsius. We will use an arbitrary value of m equals 3 in this example. Let's plug these values into the equation. Solving the equation, we get an acceleration factor of 11.572. Recall we determined 21,900 cycles for the life of our widget. Solving, we get 1,829 cycles. Quite a difference in cycles when applying an acceleration factor, am I right? Let's go ahead and cover another example. In this example, we will accelerate a temperature humidity test. Pictured is the Arrhenius-Peck equation for accelerated temperature humidity testing. Once again, AF is acceleration factor. RH op is the operational or field relative humidity. RH test is the relative humidity for the test. P stands for the Peck constant. And the rest of the equation is the Arrhenius equation, as we already covered previously. I think you already know what time it is. It's time for another example. In this example, a widget has a maximum operational environment temperature of 30 degrees C and a relative humidity of 50% RH. The widget is capable of safely operating up to 150 degrees Celsius. Wow. Engineer Bob wants to make an accelerated test that will validate a predicted life that the product or widget will survive 10 years of operation. Let's go ahead and plug in the values we just learned about in the equation. RH op equals 50%. RH test, we're going to assume, is 95%. P equals 3. Our apparent activation energy is once again 0.5. But remember, this is an arbitrary example. Don't go and plug this value in arbitrarily into your product's temperature accelerated test. So don't blame me if you're an idiot and you still use this value anyways. T2 equals 95 degrees Celsius. We're just selecting this value. We go up to 150, but we're going to assume that we have limitations with the current chamber we're using, and so we're going to stick with 95 degrees Celsius. And T1 equals 30 degrees C. Let's go ahead and plug these values into the equation. Okay, we end up with an acceleration factor of 201.104. Wowzers, that's a big acceleration factor for this test. So recall 10 years, which comes out to 87,600 hours. And the test time, when we plug it in, our acceleration factor to the 10-year hours duration, comes out to 435.6 hours of test time, or 18.15 days. Once again, wow, what a difference an acceleration factor can do in speeding up learnings on testing your product for life. Let's go ahead and change things up a bit for our final example. Pictured is the time compression equation for compressing test time for a random vibration test. This equation uses a ratio of the field emission time over the test time equal to the ratio of the test GRMS over the field emission GRMS, with an exponent for that ratio that is representative of the stress versus number of cycles curve, or the SN curve. I already covered GRMS in a previous video, and I will be doing some additional videos on vibration testing, so keep an eye out, but let's do a quick refresher. Recall, random vibration is plotted on a graph as PSD or ASD, which is power spectral density or acceleration spectral density, versus frequency. PSD and ASD mean the same thing, but some folks may be more familiar with one acronym or term over the other, so I list out both here in this example. GRMS is the total acceleration content of the vibration test for all PSD and frequency breakpoints, which is found by calculating the area under the acceleration versus frequency curve, or the PSD versus frequency curve. Now that we've performed a quick refresher, let's get back to that example now. For this example, we will use a widget which is expected to have a life of 10 years when exposed to a vibration environment, with a GRMS of 1.1 GRMS for 6 hours per day. We want to create a vibration test that will predict the widget's ability to meet the warranty target in the shortest amount of time possible. Let's go ahead and solve this bad boy. For this example, we know that T2 equals 21,900 hours, which is 6 hours times 365 days times 10 years. T1 is the test time that we need to solve for. And for V1, we will use 2.2 GRMS. Many standards will say that you cannot exceed, or you shouldn't exceed, a ratio of 2. So we are adhering to that rule of thumb in this example. And recall that our mission profile is 1.1 GRMS. We're going to use A equals 8. Again, like I talked about a few times earlier, this value is something you need to determine for the materials you are testing. 8 is just an arbitrary value that I'm using in this example to show you how the equation works, so keep that in mind. Alright, let's go ahead and plug all this stuff in. We come up with a test time of 85.55 hours for our T1 value. Now all you gotta do is scale your GRMS from 1.1 GRMS to 2.2 GRMS and run the test for 85.55 hours. Now if you have a boring job and you have all the time in the world, go ahead and do a hand calculation for all of these breakpoint PSD and frequencies to come up with your 2.2 GRMS. For the rest of us, however, that have real work to do, we're gonna go ahead and plug it into any modern vibration test controller, and that has a scaling function that will bring up each PSD and frequency to equal 2.2 GRMS based on our original 1.1 GRMS profile. This is perfectly acceptable, and by saving this time, now you can focus on accelerating other types of tests. And that's it, folks. Some key takeaways from this video are: don't use cookie cutter values or exponents and constants such as activation energy, or for the stress versus number of cycles or SN curve value. Know your material's properties and choose accordingly for your value or constant. Don't use cookie cutter values that you find on a Google search, or you may under or over accelerate your test and get unrepresentative or undesired results. Don't use more than one acceleration factor and only test for one failure mode type. You don't want to test for multiple failure modes and test conditions simultaneously. Otherwise, you cannot correlate life data against a stress input. Be careful with using parametric binomial equations to reduce sample sizes and then applying an acceleration factor to decrease the test time, especially if you're using stress levels from a test standard. If you do not know if a test profile from a test standard has an applied acceleration factor already, or do not know the acceleration factor, you can end up producing unrepresentative test results or field life predictions. Don't get carried away with acceleration factors. Make sure you do not increase stress levels to the point that you produce failure modes that you would never see with your product in the field. For instance, you do not want a part to turn into a pile of dust because you created stress levels that would be worthy of qualifying a component for a rocket when you are just testing a consumer product. Thank you for watching this video. I hope you enjoyed it. And if you have any questions or comments or need help with acceleration life testing, feel free to reach out to me at one of the links below. I hope you enjoyed this video, and if you did, don't forget to hit that like button and subscribe to my channel. Thanks for watching and enjoy the rest of your day.